So now let us take some questions related on or based on Diophantine equations. Of course, the first question is talking about determine the solution in integers each of the following Diophantine equation. So this you can do easily, or even you can check whether the certain set of uh, equations possesses some solution or not. Okay, and that is determined based on if the greatest common divisor of A and B divides C. Okay, in equation AX plus BY equals to C. Then we have a second question also. They wanted positive integers as solution. So this you can also do by imposing certain condition on them. So first and second you can do very much. There is, I think there is no problem. But for third, let us see how we can proceed. Question number 3. So they are telling that if A and B are relatively prime, and then prove that the Diophantine equation has infinitely many solutions in positive integers. So given that the greatest common divisor of A and B, of course, they are positive integers. Otherwise, I would have written mod of this. Okay, but anyway, greatest common divisor of A and B. This is 1. It is given. Okay, and 1 is the number which divides every integer. Okay, so it divides C. Therefore, AX minus BY equals to C has a solution. Okay. And let us assume that let X naught to Y naught is a solution of AX minus BY equals to C. So AX naught minus BY naught equals to C. Because X naught Y naught is solution, so they must satisfy the equation AX minus BY equals to C. Okay, and also we have learned in yesterday how we can calculate other solutions if one solution is known. So how we can calculate other solutions? Also, the other solutions, are given by X equals to, what was the formula? X equals to X naught.
Plus
Yeah, plus V by D. So here, in case of plus, we have a minus V. So we can write B by D times T. All right. And Y equals to Y naught minus A by D by T. But the thing is that D is equals to 1 equals to greatest common divisor of A and B. And also T is some integer. Okay. So what we have X equals to X naught minus BT, and other solution is value of Y is Y naught minus AT. So for positive solutions, for positive solution in integers, we must have X naught minus BT greater than 0 and Y naught minus AT greater than 0. And this holds if X naught and is greater than BT, that is this by B. Okay, and y naught by a is greater than t. We are assumed that a and b are non-zero. Okay. So this should be, I think, greater than. It is okay. I think it is okay.
माइनस का प्लस आएगा
Hello.
x इक्वल
Sorry.
x इक्वल x
Hello.
नॉट वाले फॉर्म में माइनस का प्लस आएगा
Where here?
x इक्वल x नॉट माइनस bt प्लस bt आएगा
Why?
Yes, sir, x naught plus bt greater than 0.
क्वेश्चन तो नेगेटिव में है.
Actually, in our equation, we have a negative b here, you know, here, you see. Here we have negative b. So
Yes,
of course
sir.
you could write ax plus minus b times y equals to c. You can write like this. Are you getting what I'm trying to say?
yes sir
Yes.
Okay, so I think everything is okay as of now.
Yes, sir.
Okay, so t should be less than x naught by b and y naught by a. All right. So there are two conditions, in fact. So what we can do here, so t is less than x naught by b, and also t should be less than y naught by a. So altogether we can write. So if we assume t is less than minimum of y naught by b, y naught by a, and x naught by b, then x equals to x naught minus bt. So for common t, if you are taking, okay, if you are taking some t such that which is less than both, minimum of both, okay. So if it is less than minimum of both, it means suppose this is something 100 and this is something 102. So if it is less than 100, then certainly this is going to be less than 100 by 102 also. Are you getting what I'm trying to say? Whereas if I say that it is less than, I am taking it is less than 102, it doesn't mean that it is going to be 100 less than 100. Okay, so we need to consider the minimum of these two. Okay, so then in this for this choice, we must have this greater than 0 and y equals to y naught minus 80. This is also greater than 0. Okay, and for this choice, for these choice of t as in star, we have infinitely many solutions in positive integers. Okay. Hello. Okay. One more. Yeah, one more result is there. Of course, I kept it here. The Diophantine equation. This is solvable if and only if greatest common divisor of A, B, C divides D. Okay. So let us start from here. So next is their next result. Of course, you can generalize it. Okay. The linear Diophantine equation. The linear Diophantine equation. Diophantine equation. Ax plus by plus cz equals to d is solvable if and only if greatest common divisor of A, B, C divides D. So this is the this is a result, okay? Or in general, suppose AI and there are variable xi equals to, suppose I'm writing D or C, we can write, okay, let us write C equals to C and I equals to 1 to N. In general, the equation, and moreover, because we are interested in integer solutions, so this is a linear Diophantine equation, is solvable if and only if greatest common divisor of AI divides C. Okay. So this is a result. When we say that this linear Diophantine equation, it means we are interested in positive solutions. Otherwise, there may be so many solutions in real numbers, okay? But we are interested in positive solutions only. So let us see how we can prove the in case of 3 variables, okay? So there are 2 parts. First part is that if this is solvable, then greatest common divisor of A, B, and C should divide D. Okay, so we can assume. Let us assume greatest common divisor of ABC is equals to something E, or let us see. Okay, greatest common divisor of A, B, and C is equals to suppose, for example, E. Okay, so this E should divide A, E should divide B, and E also divides C. So there exists integer P, Q, R such that because E divides A, E divides B, E divides C. So this is equals, so A equals to we can write some PE and B equals to QE and C equals to RE. All right. Okay. So what we have assumed in the starting that this is solvable. Okay, this is solvable. So let AX plus BY plus C Z equals to D is solvable, and X0, Y0, Z0 be a solution of this equation. So we have AX0 plus BY0 plus CZ0 equals to D, because the X0, Y0 and Z0 is a solution of this equation. All right, and now let us substitute the value of A, B, and C from here. Okay, from 1. So we can write, using 1, we can write BEX0 plus not B but P. This is P. Okay, PEX0, and then we have QE Y0 plus C. In place of C we have RE Z0 equals to D. Okay. So what we can take common? We can take common E from here, and then we have Px0 plus Qy0 plus R Z0 equals to D. All right. So what we conclude from here? What we conclude from here? This means that
E divides.
this E divides D. E divides D. All right. So one part we have proved. The second part, conversely, assume that E divides D. E divides D, then we need to prove that the given equation is solvable. Okay. So E divides D, and E is the greatest common divisor of A, B, and C. So there exist integers x0, y0, z0 such that E equals to ax0 plus by0 plus c z0. Okay. Now since let us, this is number 2. Since E divides D, so there exists some integer t such that, so for some t belongs to z, we can write Et equals to d. Okay. So in equation number 2, let us multiply throughout by t. So we have Et equals to a x0 t plus b y0 t plus c z0 t. And the left hand side then becomes d. And the right hand side, then this implies that d equals to, in the right hand side, we can take t as common. In the right hand side, we can take as common. So we can write ax0 plus b y0 plus c z0 times t. So everything is okay or what? No. We can write, no, we need not to take common. Okay, we can write it like this: a x0t plus b y0t and plus c z0t. Okay, fine. So this we can write a x prime plus b y prime plus c z prime. D equals to. So it means x prime, y prime, and z prime satisfies the given linear Diophantine equation. Thus, x prime equals to x0t, y prime equals to y0t, and z prime equals to z0t is a solution. Of the given linear Diophantine equation. Okay. So this is done. Fine. And other problems, if you see, let me show you other problems here. Where is that? Yeah, this or this you can see. Okay. Actually, I have two versions, so that's why this question was not copied there anyway. So we have done this one. They have given some other hint to solution of this question that if A and B are relatively prime positive integers, then this dipentine has infinitely many solutions in positive integers. Okay. Then question number 5, question number 6, question number 7 and 8. They are word problems. You can read them and you can try to figure out what is question you are going to get. Okay, and then you can solve. Just we have done one question yesterday. And if you have any problem, you can tell me, then we will discuss in class. Okay. So they have similar kind of, you will be getting, in all cases, you will be getting a linear dipentine equation and you have to solve them. Thing is that you have to read the question and keep them in mathematical form. Okay, and then you can solve. All right. So next thing is that primes and their distribution. So something we are going to discuss today. You know what are prime numbers? Anyone? What are prime?
The numbers which are divisible by the number itself and one only.
Okay, so you say that first of all, they should be integer, huh?
Yes.
And, okay, so one is prime or what?
And the number itself. For example, 2, 5, 6.
One is prime or not? Hello? One is prime or not?
Not. Not.
No. No prime. Okay. So 2 is prime. 3 is prime. What about -2 and -3? They are not prime. Negative number never prime. Okay. So definition, official definition, if you can see, then you will be seeing that in the definition itself, they are taking that this should be greater than 1. Okay, so this is naturally is going to be positive integer. Okay, a prime, a number or integer like this. Okay, an integer p greater than 1 is said to be prime if its only positive divisors are 1 and p itself. Okay. So here we are defining it with the help of only positive divisors. Okay. And of course, if you are taking any number n, it is going to be divisible by 1 and as well as -1 as well as n as well as -n. At least you will be getting this much. But while defining prime, we are taking consideration of only those divisors which are positive. So this is a very crisp definition, one should remember. Okay, so -2, -3 not prime, -100 not prime, -17 not prime, -7 not prime, -5 not prime. Okay, fine, it's all right.
Yes.
Okay. So next thing is that if you see, now we know what are prime. So next thing is that to count the prime numbers. Okay. So there is a function defined. Okay. A prime counting function. We call it prime counting function. And we also estimate our growth, the primes, by upper bound. Okay, so prime counting function, it is denoted by pi. Okay, it is denoted by pi x kind of symbol. Prime counting function. Just a minute. For any real number x greater than 0, let pi x denote the primes p less than or equals to x. Okay. And thus pi of 1 is what? एक से छोटा या बराबर कितने प्राइम होंगे?
0.
0.
2. Pi of 2 less than or equals to only 1.
1.
केवल 2 ही होगा एक प्राइम. What about pi of 2.5? 1. Less than or equals to 2.5, and we need to find the prime. Okay, pi of 3.
2.
एक तो 2 होगा, एक 3 होगा, so 2. Okay, and similarly pi of 7 by 2. 2.
2.
Pi of 10. 2, 3, 5, and 7. 4.
4.
Like this. So this is pi of x is a prime counting function. Okay. All right. So of course this is not 1, 1, you know, because 2.5 and 2 both have the same value, but pi of 2 and pi of 2.5, but 2.5 and 2, they are not same. Okay. Okay, let us see some results on prime distribution. So there is a result distribution of prime on distribution of prime. Distribution of primes. One result you must be knowing that every integer can be written as a product of prime. In fact, every natural number, huh? Whatever number you are writing, suppose you are writing 10, then you can write 2 times 5. Okay, you are writing 100, so you can write 2 times 5 times 2.2 times 5 like this. Okay, you can write 2 square into 5 square. So this is a product of prime numbers. If you want to 1000, then you can also write it like this. Fine. And if you want to suppose you want 70, maybe 72. If you want 72, how you can write 2 times 36, or you can write 2 times 18, 2, 8, and then 3 square like this. So 3 square into 2 square. So 3 and 2 are prime. I think 9. 3 cube, 2 cube, huh? 2 cube, 3 square, 2 cube. Like this. So every natural number can be written as a product of primes. So this is a fundamental theorem of on prime numbers. Okay, let us see what are the results in distribution of prime. So there is a result. In fact, this is a very old result. Sometimes it's called Euclid Theorem. So there are infinitely many primes. This states that there are infinitely many primes. Okay. So we prove it by contradiction. Proof by contradiction. Let us assume that there are only finitely many primes. Okay. Suppose they are P1, P2 up to Pk. So there are k numbers, only k primes. Okay. Now consider their product P1, P2 dot up to Pk, and let us Pk and plus 1. This is equals to M. So of course, because Pk are P1, P2 up to Pk, they are prime. So their product is going to be an integer, and when we add 1, this also be an integer. So M is an integer. Okay. Fine. Since M is greater than 1, of course, we are adding 1 here, and P1, P2, Pk, they are prime. So Pm is certainly is going to be greater than 1. Okay, greater than 1. So by fundamental theorem of arithmetic, implies that it is divisible by some prime p. Just I was telling that every positive integer greater than 1 can be written as product of prime numbers. Just I have illustrated with certain examples. I've written 110 and then 72. Okay. So if that number is a product of primes only, so they will be divisible by those primes. All right. And since here in our case, M is greater than 1. So by fundamental theorem, it is a product of some primes. And certainly this is going to be divisible by those primes. And let us assume that let is P be a prime, such prime, which divides M. All right.
तो समझ नहीं आया.
Hello. You are
Yes,
not
sir.
getting okay. Actually, okay. Let me write like this. Okay. So if M is some natural number greater than 1, so by fundamental theorem of arithmetic, this is going to be product of some Q1, Q2 up to Qs. Are you getting? Hello.
Yes.
So if P is some prime here as a product in this of M, okay. If M equals to Q1, Q2, and P is somewhere, so P should divide M or not? Hello.
Yes, sir.
Just like if you're writing 10, 2 times 5. So 2 should divide 10 or not? 5 will also divide 10. Fine.
Yes.
Okay. So since m is greater than 1, so this is, of course, this is a natural number. So by fundamental theorem, this will be product of some primes. Okay. And there should be some prime p which divide m. So that's what I'm telling. Is it okay? Now you got? And let me show you if there is some fundamental theorem of arithmetic. Okay, let me show you. You can see this theorem also. If p is prime and p divides a b, then either p divides a, p divides b. Okay, let me show you here is fundamental theorem of arithmetic. Every positive integer greater than 1 is either a prime or product of primes. This representation is unique apart from order in which the factors occur. Is it okay? So if p is prime, then all right. If it is not prime, then we can write that number n equals to p1, p2, p3, dot dot dot. Okay. ठीक है? चले आगे.
Yes, sir.
Okay. So here we have. Okay. So here we have some prime p which divides m. So by our assumption, since there are only k primes, we have assumed that there are only finite number of primes. K primes, namely p1, p2 up to pk. So because there are only k primes, so p must be 1 among these. Is it okay? जब केवल k प्राइम्स ही है तो p अलग से थोड़ी आएगा, उसी में से कोई होना पड़ेगा, है ना? पक्का?
Yes.
हेलो
Yes.
हेलो
Yes, sir.
Yes, sir.
प्लीज डू respond. Okay, so p must be among these. Okay, and so p must divide their product too. So p must divide p1, p2 up to pk, because p is among these p1, p2 up to pk. Okay, fine. Also, since p divides m, so p must also divide uh, uh, the difference of these two, p1, p2, pk, and m. Okay, so p should divide m minus p1, p2 up to pk. All right, and that is p should divide 1, which is a contradiction because p is prime. So and p is prime, so p should be greater than or equal to 2, so p cannot divide. Okay, which is impossible. Therefore, our assumption is wrong. And so there are infinitely many primes.
Thank you for watching this video. To stay updated, please subscribe to our YouTube channel, Cosmos Learning. Happy learning through Cosmos Learning. To watch more, click on any of these cards. Thank you once again.